You see, not all answers are meant to be found. Some are meant to be carried in the journey, shaped by time, by wonder, by the strange business of being alive. Today's conversation is not about having it all figured out. It's about tracing the outline of the unknown with someone who's chosen not only to walk that path, but walk towards the mystery, not away from it, deeper into it. I'm Bhavidhir V. Bharadwaj. Welcome to episode 44 of Genesis of Tomorrow. The following is a conversation about quantum natural language processing, conceptual spaces, categorical theory, philosophical provocations, personal anecdotes, and much more with Dr. Srinjoy Ganguly, a seasoned, a very seasoned quantum researcher. Also, folks, if you're interested in such deep science and deep tech conversations and are able to derive even the slightest bit of value from the show, please support us by clicking the subscribe button so that we can keep improving the quality of the episodes and keep on bringing such wonderful guests over for you. Now, without any further ado, let's get right into it. Enjoy and thank you. And we're rolling now. So, first of all, Dr. Srinjoy, welcome formally to the show. Before anything else, in your work on quantum NLP, what exactly does a normal semantic sentence look like or feel like or whatever it means to a quantum machine or system?
So that's an interesting point, and it's an interesting subject. And I was working in quantum NLP, I think around like 2 or 3 years back, and I myself found it very fascinating that like you can now represent these sentences which have a particular grammatical structure, right? Like because sentences or language itself is ruled by grammar, and then you take this grammar and now you can make this structure as a quantum circuit and run it on a quantum hardware. That idea itself is really beautiful. But what happens is like in a sentence, you have nouns, you have verbs, you have adjectives, right? All these stuff, and you want to bind them with grammatical rules, right? And when you start binding them, then it sort of forms a string diagram, and now this diagram can be converted into a quantum circuit, and that's what the quantum NLP is about. But this kind of field, like this kind of configuration which I'm talking about, this is more from a uh, categorical theory point of view. So I'm not going deep into category theory, but understand that it's a type of abstract mathematics from which we derive these kind of like we form these rules as diagrams, and then we can convert these diagrams into quantum circuits. So in simple terms, so in quantum NLP, so you have these words, each is like a quantum state. It's like it's situated in a Hilbert space, right? That's why we call it distributional. So it's distributed, these words are distributed in the space. And now like now you uh, combine them. Basically you combine them with cups and caps, so we call cups and caps. So these cups and caps are nothing but just concave or concave shaped strings, and you can use these strings to then combine these distributed words present in the Hilbert space. And these combination, these cups and caps, are basically the entangling topology. So you can basically entangle these now with the help of these cups and caps. And once you entangle, then you get a register which is like your main sentence where the essence lies. So let's say Alice gives Bob. So there is an action of giving, and then so Alice is the noun and then gives is the verb. So your essence will lie in this verb, gives, but you can entangle Alice with the word gives, and then you can also entangle Bob with the word gives. and only then the meaning will be appreciated, right? And once you do that, then you form a circuit out of this diagram, and these entangling strings, they become C naught gates, like your bell pairs, simple bell circuit for entanglement. And once you run it, then you obtain the logits, or like a similarity score between the meaning that you want to infer. And then once the sentence collapses to that register, the verb register which I was talking about, then you can measure the similarity very easily. And that's what a sentence is to a quantum machine. So a sentence is nothing but a diagram converted into a quantum circuit via help of circuit rules like ZX calculus. So ZX calculus is a formalism like where you can convert these diagrams, these grammatical diagrams, into quantum circuits and then run them on real quantum hardware. So already, I think recently some work came out, and they have also ran a larger data set of English language on
Hmm.
an ion trap based hardware. And previously they have tried with the superconducting qubit. So most of the work has came out from Bob Koech's research group at Quantinuum. But before that, he was already conducting this research at Oxford when he was a professor. So I feel like that's the essence. And then once you get the outcome, then you do a typical classical machine learning phenomena, like optimize it with classical optimizers, feed it back and change the parameters, because ultimately the words are the states, and you are like representing them with unitaries, rotational gates. And you can use separate like different sorts of ansatz for doing this. But that's how you get a sentence for a machine. Now you might think like, okay, what are the advantages of doing it in this way? Because then there is another part of quantum NLP community which is focusing on taking inspiration from classical models. So let's say quantum transformers. So transformers, we are aware that they are those like deep neural networks which power our chat GPT like systems. But then we are talking about quantum transformers. So we directly took an inspiration from transformers and converted it to quantum. So that's another part of quantum NLP. And then this quantum NLP is something which I have worked on, and Quantinuum is working on, and it's very promising as well. And so
Just to,
you have this.
yeah, yeah.
Sorry,
Please
yeah,
go on.
please.
Please go on. Please go on.
No, so like, I mean, I was just thinking about some advantages on this, like just like to comment on, because like what's the most like question which I get is, okay, like why do you do it like this? Like you can do quantum transformers and get it done, but then the advantage is like then you can get some sort of an quantum advantage in this way, because uh, quantum, this kind of formalism, category based, this is inherently quantum, because ultimately when you make these string diagrams, they can contract as tensors. So they are essentially tensor networks, and tensor networks are highly compatible with quantum computers, because you can treat quantum circuits as tensor networks as well. So that's why this quantum hardware gives you that tensor contraction for free. And then why not utilize it for the grammatical structure that we already have for our languages? And but some of the bottlenecks are that, yeah, noise is of course, like most of the bottlenecks come from the hardware that we have right now. But once that's gone, then like, and let's say like we have logical qubits, then the depth of the quantum circuit that grows with the sentence length. So that's a problem. So even for simple large sentences, the depth is huge. So like the focus should be on like how can we reduce this depth, because imagine, like you want to encode a full paragraph. Imagine the quantum circuit depth of that full paragraph of a book, or maybe a whole page in a book. That's huge. And then another bottleneck is the parsing assumption, the way we parse. The parser should be set with certain types of rules, so you need to have those rules there. uh, Otherwise it breaks down.
That was exactly what I was coming to actually. Like, why not go down just quantumizing transformers. But okay, maybe a little about category theory. Why do we need to use these compact closed categories in order to get quantum NLP working?
Yeah, because so it's like, so answer is more technical and mathematical. So I mean, you have to write maths and then prove like why you need compact close. But like, if you read up on the literature, then you are going to see that these compact close categories, they come from a field called categorical quantum mechanics, where all the quantum mechanical phenomena that you read in a physics book or in a quantum mechanics book, you essentially get to do them with categories. And categories are nothing but like, you can form relationship or morphisms between objects, different objects. So you can say that uh, it's a more extended or generalized version of relations and functions that we study in our school. So even categories also have, like, let's say if you have one object, you denote by an oval. If you remember in school, we used to do it. This is one object. Then there is another set A, set B. But here we are calling them objects. So we change the names and we make it more generic. And then we used to draw arrows from one of the set to another set to show relation, right? So even categories are also formed like that. And then we form something known as compact closed categories, which, like, Bob and other researchers later saw that, okay, like, this is actually grammar. And Lambeck, the linguist, like Lambeck, Joachim Lambeck, he actually said that, look, this is grammar, because they were all category theory pioneers. So they can see that, like, when you make these relationship between objects, that means, like, you can also, you're actually doing grammar, because in grammar also you are making relationships between different words, and from that you're getting the meaning. And then you can learn that meaning from this context, like gives. So if you have several sentences with gives, and with the word gives, like the verb gives, and then you also have different verbs like loves, hates, then this context can be learned with the help of a quantum computer. And that's why like this model is like what we call as quantum native. So this model has a name which is known as discocat. So distributional aspect, which I mentioned to you before, so it ties to that answer what I gave you previously. The words are distributed in that Hilbert space, and they are compositional because now you can compose them with these diagrams, with these strings, and categorical because they are forming compact closed categories, and that comes from categorical quantum mechanics. So that's how it relates. So that's why, like, when people study this subject, they study some basics of categorical grammars. So categorical is related to the quantum mechanics part, but categorical is for the grammar, like the pre-groups. The pre-groups can be these nouns, pronouns, verbs, and all these grammatical constructs that we study. And then we use lambic calculus, which is the set of rules that defines the English grammar.
In the current sort of NLP in classical domain, there is this new thing where we are trying to skip the entire tokenization process by
Hmm.
using LCMs, large concept models. Is the idea of not having the model or system individually look at these tokens, but rather understand the context, the conceptual context of a particular semantic structure? Is that something that quantum native systems, QNLP based systems, have an inherent advantage to some degree in? If yes, how exactly the mechanisms of that particular advantage work? That sort of a qualitative analysis of sorts.
Um, I am not fully sure, but like what I can understand is that, like, the quantum theory explains the contextuality, and it's really really good at doing it naturally. Of course, when you use this the notion of category theories, then I think, like, it's you can easily tokenize the words which lives in a Hilbert space, and then you can do relationships between them. But then, like, in that, like, you can say with those tokens there should be a certain order, right? Because then grammar follows a certain order. You need to do the things in an order, and you can also define order in other ways. So it has been also seen through experiments that quantum is really good at learning the order as well, that in which order the sentences should be for the grammar, and not the other way around. So it kinds of gets it automatically through these tensor contraction rules. So I feel that's one of the concept to look at. Then there have been some recent developments. I didn't get the opportunity to go through everything, but the extended version uh, of Disco Cat, which is known as the Disco Circ. So it's distributional compositional circular. That is helpful for these large amount of tokens, because Disco Circ is actually for scalable QNLP. So Disco Circ is specifically for um, like you want to encode a full paragraph or a full page and run it through a quantum computer. But then the quantum computer should also remember what happened on page 2 and connect it with what's happening on page 13, right? It's a story which flows. Disco Circ allows that transition. But of course, as I said, the bottlenecks, it's the circuit is too large, and the researchers are working to reduce that. But some of the initial experiments of Disco Circ have been run. I think they were run last year on iron trap hardware.
In terms of uh, okay, a hypothetical question of sorts, but in terms of trying to generate creativity in relation to human speech, the large language models, if you tell ChatGPT maybe to generate a poem, it is able to, but again, the lacking aspect is that of human ingenuity or creativity. It's not a creative thing. Almost all the prompts telling you to generate the poem and the poem generated therefore by the model, they are somewhere or the other on a similar template. You can feel that okay, it's AI generated. How far are we to, or how close are we to a quantum machine that can write poetry not from entirely training, but rather maybe just from intuitive coherence in terms of its understanding of the semantics of a language?
That's, I think that kind of thing which we're looking at, like generating poetry, like of course with classical models we can do it, and yeah, and you're right, like we can see it's AI generated. But for quantum to do it more intuitively, I think are we are a bit closer to that right now based on the developments of Disco Circ which has been happening recently. So I feel that like once we crack Disco Circ, once we know like how we can reduce the circuit depth and run on a quantum computer, I feel that, and of course the hardware matures as well, because we will need logical qubits for that sort of thing. I think then we will see some real applications of quantum NLP for generating poetry or generating other sort of creative works. Because if you think about it right now, like we are training quantum computers on simple sentences, and the sentences need to have a specific structure. We have not deviated from the structure as much, but we need to deviate at some point, right? Because then if you see like I think, so if I remember, we like many experiments were done with context free grammar, so which are very easy, like these kinds of sentences like Alice gives Bob, Alice hates Bob, Alice loves Bob, like these kinds of sentences where you have this noun and verb and maybe some adjective as well, very simple sentences. But then if you try to, because the poetries are very complex, right? Poetries have different sorts of elements in it, and then in that sense then you need to have your quantum computer learn through a few poetries as well. But then the rules that embed those poetries, that makes the circuit very large once you convert that to run on a real quantum hardware. And that's why we need fault tolerant hardware if you want to reach that stage. So it's closer, but also not very close that we can achieve it within 1 or 2 years. It's still going to take some time, because the most beautiful thing was that we were able to run a language, or this model like quantum NLP, which is based on abstract maths like category theory on a quantum hardware. That itself is a breakthrough, right? Because it has been never done before. And which means, like, if we keep developing on that, then we will be in a stage very soon where we will be able to develop beautiful poetries, and quantum will be more creative, right? Because the rules of quantum, they seem very mysterious, though we understand like what's happening, but still at the same time we also do not fully understand what's happening in a quantum system. It's very, very complex also at the same time. So I think then the quantum can take advantage of its properties like interference, superposition, and its ability to contextualize stuff beautifully through tensors. I think these things will uh, play together when generating that sort of poetry, which we don't find in transformers, or in like any classical chat gpt model, because there, like, the context has to be learned, right? Like, you give a corpus of data, like really large data set, and then like it has to struggle, like it struggles to learn everything, right? Though it's doing a nice job, but quantum will make it more easier.
It also, again, as you very rightly put forth, in terms of trying to generate creativity or mimic creativity for that matter for systems, it is very substantial to contextualize whatever you're putting out. I mean, sarcasm or metaphors, giving analogies, it's all contextualized. For classical models, it's like we have to lay forth the entire foundational basis for them to do that. Whereas for quantum side of things, as you explained, even in the technical aspects of it, it's just in general better at trying to understand or even by itself generate context before generating the semantical structure.
It
And
should be like, sorry,
yes,
sorry, yeah,
yes, yes,
please
yes,
go
yes,
ahead.
yes. No, no, please, please, please continue.
No, no, no. Like the question which you're asking, I feel that like in general it should be better at understanding the context, because actually that is the meaning of categorical grammar. It should be able to get the context with a few sentences. It should not need huge data sets like how we need for classical. And actually that's the meaning of quantum. Like in quantum ML research, we talk about this issue, that why do we need like so many data points? Like, let's say we are training on images, and you can replace the images with sentences, of course. But then, like, why do you need like millions of images or like millions of sentences? No, it should be so natural. The construction, how we form mathematically, that should be so natural, and it should be so quantum native. That's what we call for disco cat or disco sir. It should be really quantum native, that quantum computer automatically generalizes the context. So like it's like human brain, like you see a picture of dog, it could be any breed, but then you see other breeds of dogs, and then you immediately recognize, like our brain immediately recognize that yes, it's a dog, but of a different breed, but it's a dog. The essence remains, it's a dog, we know. But then how can we achieve that with quantum? So that's also a research in quantum ML. So it connects to quantum ML somehow, that like we should need lesser amount of data to contextualize and generalize that contextuality.
Is there also somehow the aspect of, is it similar to how human brain works, or in terms of its closeness to how the human brain works? Or is it maybe a different way, a black box of thoughts that is generating the same output kind the human brain generates? Like, is the are we at a stage where, at least in quantum natural language processing, we can say that it is far more closer to the way that humans perceive speech understanding? Is that understanding part something that we have been able to develop or build right now?
Yes, we are going towards that. We are going towards that understanding, because human brain has that cognition system which is deeply interlinked with speech, with language, right? Like how we communicate. Because even if you see like ancient humans, first we tried to communicate with drawings, and then we started speaking, like we started using our throat to show some sort of action or speak something, right? And that's how the language emerged slowly. So we are actually trying to get to that stage, because so if I remember correctly, I mean, now it's been a long time again for me, but there are papers that connect quantum NLP with quantum compositional intelligence. So that's a research which Bob is actively pursuing in Quantinuum, and that actually goes in this direction, like how we can convert these aspects of quantum NLP that we have, and how, it ties to cognition, it ties to consciousness. Like, it's it sounds very philosophical or sci-fi or something, but it's not, because like then once you have this kind of a compositional model, then what you can make is a quantum compositional intelligence model, which can understand context better. It can understand, with a very few amount of data points, that what is the context of a whole paragraph or a page or something. And then, it can generate its own understanding of the subject, maybe, which is not even understood by humans, but it can generate a completely new context. We never know. So that's why, like, it's good to explore, and I think this research is in a really nascent stage right now. Developments are happening very slowly, because there are papers I was looking at 2 to 3 years back, where researchers are using like ZX calculus and its different variants like ZW calculates and so on, to model phenomena in consciousness, like how we perceive things, how we understand them, like what's the connection between them, that sort of thing. They were doing that with diagrams. So I feel that, this has a huge potential, transitioning from speech to cognition, or to understand how the consciousness works in general.
There has not been, as you said, it's in nascent stages, but even at large, there hasn't been any very implementable product that the masses can maybe interact with, and thereby there isn't any, I would assume, any solid research upon or test phase of how it puts up against the Turing test. But I'd assume it will be able to surpass it pretty easily after all that
I
we talked
think
about.
so. I mean,
Yes.
I believe in the tech. I am a tech person.
Hmm.
I believe in the tech, and I studied this tech, and that is why it interested me, because this this notion of using something from the math and then implementing on quantum hardware, which is also native to quantum, and not like, artificially doing, or not like, taking blind inspiration from classical and just implementing it on quantum without thinking that what could be quantum native. So I feel that this has the promise. But yeah, as you said, right now we don't have a product on like quantum compositional intelligence or something. This is more like a theoretical framework. But the thing is, like, then for every product you need to start from theory, right? You need to start from theory. Then, like, you are going to design some structures, some algorithms, and then once you reach that stage of algorithms, then you start running them on the hardware and see that whether they really worked or not. um, and then, like, then the question will come later on, and this is what I envision, of course. And maybe it might be completely different, because this is like predicting the future, and future is always uncertain. But the thing is, like, then once we have, let's say, an algorithm which mimics, let's say, cognition, understanding on like how humans understand any concept or anything, then I think at that point, like, maybe like quantum computers will be able to talk to each other, just like how humans talk with each other, with the help of this inherent like quantum compositional intelligence model. That is what I envision. And uh, and it's kind of already happening, like, because when you have larger number of qubits, you put them in different dilution fridges, and you want to network them, right? So you want them to talk to each other, right? So that you can use their properties more efficiently. So I think at a certain point, like, when these quantum NLP models are very mature, like, let's say we have reached the stage where now we can encode a full book into a quantum hardware, and then, like, able to extract some meaningful information from that book. I think at that point of time, then we will be slowly transitioning into compositional intelligence, where now we can combine the information of other books in a more intelligent way, in a more quantum friendly or quantum native way. That will be, like, I think, one of the first sort of products. It remains to be seen, like, what sort of applications we will get into in the future, if some sort of product comes out of QCI, quantum composition intelligence, but it will go towards AGI at a certain point, artificial general intelligence.
You said that you were working very closely in the field probably 2 3 years back, but right now, what is the most intriguing than that you're doing?
Every field is intriguing in quantum. I'm always happy to work on different fields, because I was working, like, in 2021. I was mostly working, like, exploring quantum NLP and QCI and that sort of stuff. QCI was, like, more nascent at that time. Ideas were there, but yeah, like, the papers were really less. But then, like, in my job, like, then I was focusing on something different and learning new things. And even right now, I still don't know all the things, because that's a lot of information. But I was working on quantum chemistry stuff, mostly related to life sciences. So you can see that's different from quantum NLP. And then I also worked on quantum ML, but that's again different. Like, quantum transfer learning, quantum convolutional neural nets, and quantum neural nets in general. Like, the quantum ML part, right? Which is, of course, there is a lot of hype on that, but let's not go into that right now. But yeah, like, that, those sort of subjects I was working. So,
How?
and right now I'm doing my PhD from UCL, and now I have shifted from all these software aspects to engineering aspects. So my thesis will be on neutral atoms interfaced with superconducting circuits via photonic integrated circuits. So right now I'm working on designing a photonic integrated chip, uh, which will be used for tweezing and trapping these neutral atoms. And then once we do that, then we interface them with the fields emanating from the superconducting resonator or superconducting qubit. Right now, the initial goal is to do it with resonator. Some of the earlier experiments have already been done, but they were with moving atoms. Like, the atoms move very fast on the top of the chip. There's a distance between the atom and the superconducting chip, but the atoms, like, they keep moving very fast. But right now, like, what I'm developing is that we will have a photonic integrated circuit, and it will be able to hold the atom on top of the superconducting chip, so that we can have a more coherent and long lasting interaction between the atom and the chip. So it's I like this because it combines three different tech: superconducting, neutral atoms. Like, I am completely new to neutral atoms. I didn't study neutral atoms before my PhD, so also this is my first time exploring neutral atoms. uh, and then photonic integrated circuits, which again I have not explored and I have never designed anything, but it's pretty fun that, like, now I get to do this in my PhD and explore three different kind of tech, which themselves are like huge domain, right? Because photonic integrated circuits are used by Xanadu, Psi Quantum. they are developing photonic qubits, right? And then superconducting is a huge world in itself, and now neutral atoms is also becoming a huge world.
I mean, a few years back, till a few years back, quantum was still, from the public perception opinion of things, it was still something that was a little not as hyped about as maybe something like AI. But today, quantum has become that buzzword along with AI and everything. So a lot of even the younger folks, undergrad people, even high school students, they get interested about, okay, you know what, we want to go into R&D in quantum this, quantum that, all different things. For the younger folks, how do you recommend them to get into research? What are the avenues to get into quantum research? How do you see the entire industry moving forth? How is it currently moving? And how can you get your foot in that door?
So that's a really nice question, and I mean, I have been asked this question by a few people before, um, and of course, like, I mean, I keep mentoring students, and even they also ask this question to me. I feel that, like, for quantum, like, right now, it's so nascent. Right now, it's like a new kind of semiconductor revolution, a new computing revolution happening. So in that sense, like, what do we do? Like, we engage with the community to learn more. I feel that still, like, there are a lot of nice resources which students can use now. uh, when I started learning around like 2017, 2018, at that time, like, I think Qiskit was just launched in 2017, and like, you didn't had many features apart from just dragging and dropping a few Pauli gates and Hadamard gates and so on, and doing some simple measurements. Um, and even running on like quantum hardware was also difficult at that time. So they just had like some simple simulators. But now the situation is very different. Like, now you can engage with open source projects, make contributions. Then once you start becoming mature, then you start reading research papers and start implementing some of the research papers for practice. I feel that that's a really good way to learn research. Once you start implementing the papers by yourself, you see, like, how the things work out, the simple things. I mean, you don't need a, I mean, if the paper talks about, yeah, we used a GPU cluster of like 1,000 GPUs or something, no, you don't need to do that experiment, obviously. Like, you can do very simple experiments because you cannot have access to 1,000 GPUs like big corporations. But the point remains the same. Like, you can still do simple experiments by implementing that research paper, right? I think that's one of the best ways, apart from open source contributions. And then engage with the community. Like, I grew by engaging with the community, uh, by solving IBM quantum challenges. They happen every year, right? uh, Solve challenges, teach others about quantum. I started my journey with education itself when I was working on my startup Adroit era. As part of that startup, I was giving faculty development programs on quantum, giving talks. I launched 2 Udemy courses, as everything was part of that startup. Every activity I did. And that was about community building in quantum, making people aware that, look, there is this tech, and, like, this tech can do some wonderful things, though it's in its beginning stage, but it's going to become bigger in the upcoming years when companies invest more in that. And I think IBM has been instrumental in this job, because they are the first ones who launched all the materials on Qiskit, made it open source so that other people can try. They made their hardware open so that you can run experiments on quantum hardware. So many papers, like so many researchers, uh, got help when IBM made their hardware open in 2016, I believe. Yeah, I think it was 1 year before Qiskit. Yeah, I think it was 2016 when IBM launched their first quantum hardware. So I feel that this is one of the way. And then another thing is like participate in internship programs. Like uh, I am mentoring at Q Intern, which is part of Q World organization. I've been mentoring continuously since 2021, and it has been a really humbling experience. I get to interview so many students. I recruit them. They work on a project, whether research or educational, like just a quantum related project, and they have outcomes. I feel so happy. Like that happiness cannot be expressed in words, because once you get an outcome, so let's say, let me give you an example. So in 2021, there was a like education project which I proposed in Q Intern, to launch a book on ZX calculus, and that too, like particularly focusing on the hands-on aspect, like the physics, like Python-based ZX calculus, which they can implement, run their own circuits, and uh, do circuit decomposition, compilation, optimization, everything with ZX. So we launched that book, and I was so happy to see that even Bob shared that book along with his other ZX books on LinkedIn. So that's an achievement. That's an achievement for my students who were working so hard for that book, right? Uh, they feel so proud of themselves that, yeah, something which they were working on, that's promoted by one of the pioneers of ZX calculus. What more do we need? Then, second, another outcome that's already going to come will be Qiskit Metal, which is again by IBM, and it's for designing and simulating superconducting qubits. So again, there was no book. The materials were available online as YouTube lectures. But in 2023, I proposed that educational project, and the book will be launched very soon. I think by August, or maybe by July, you will see the book in the market. It's already available on Amazon for pre-order. So I feel that, like, these are some of the tangible outcomes which you can count from internship programs, and these outcomes help you in your quantum research journey, in writing a book, writing a paper. I think there, yeah, I think from last year, like, there is a paper on quantum error mitigation which is currently in preparation, and we are preparing to submit it in a journal. So when you see these things, then you see that you have a lot of opportunities to interact with mentors, get in touch with them, and publish some works with them. Or even if you don't publish, just learn. In the beginning, just learn. Like, once you learn, then publishing and community building, that will automatically come, because when you yourself have the knowledge, then you can share it with others later on. And that's how many students and many people are building their profile in quantum. I myself built like this. But a small interesting story here about me is that I was not interested in quantum, to be honest. When I was in my undergrad,
Uh-huh.
yeah, in I think, yeah, in 2016, I think, I didn't knew that IBM launched quantum, and I was least bothered, really least bothered. I was just more focusing on my internships with DRDO, uh, and there I heard about quantum communication, because DRDO works on these advanced projects, right? Because they are defense agencies, so they have to do. But there I heard about it, and then I searched about it. So also, it was not quantum computing; it was quantum communication. That's how I knew that, okay, something like this exists. And then I saw, okay, QKD, teleportation, and CATs, like, the CAT 0, CAT 1. in 2016, and I was like, no, this is, I don't want this. I don't want to study this. I was like that. I was not feeling happy to see all those cat zero and everything, which even other students also, they also say that, like, yeah, it's the notation which we use in quantum mechanics, right? The Greek letters are that's spooky to them. So I was feeling the same thing. But then, like, later on, like, I discovered through that quantum communication search, I also discovered quantum computing. And then at that time I didn't know about Qiskit, because of course it was not in the market, it was launched later. But towards the end of 2016, I realized that, okay, like, this field is going to be something like AI, like how AI was developing at that time. Since 2014 and 15 onwards, uh, AI was becoming popular, data science was becoming popular at that time. And then I saw that, okay, like, quantum will be also popular in some time, so it will be good if I can at least learn some of the basics. So even though I was not totally interested, but then in 2017 I learned some of the things, some of the basics. I was more interested in signal processing at that time. So I was not interested in quantum. But anyway, I learned, but I became serious about it in 2018. From 2018 onwards, I became more serious about quantum, to be honest. So I was not into quantum, but now you can see I am in quantum.
That is sometimes the best way that you get to know what you want to do. You're doing something, you hear about something, you maybe see what it is. Sometimes it clicks, oftentimes it doesn't. But when it does click, I mean, what else would you want then? It's always a good thing to then have something that you can keep on doing with as an active interest. And
Very true.
and
I
that
strongly
is,
agree.
yes, and that is exactly why umpteen times the best way to, when you are interested in something, the best way to get to know about if you'll be able to sustain a sort of career in that particular domain is to just go deep into that particular subject matter, read the literature, try to consume as much as you can about that specific thing. If it bores you, one is the good kind of bore where you're like, oh my god, I've read three
Yeah,
papers right now in a single day on my first day one. That bore is good because I mean you are consuming all that stuff because you're interested. The other kind of bore
absolutely.
is quantum is cool, but no, I'm not reading the research papers. No, I'll just read the clickbait title on a YouTube
Yeah,
thumbnail, and yes, I'm good to go. I'm interested in quantum mechanics. No, that doesn't work. But that is exactly why. Try to surround yourself with as much as of scientific literature of that particular subject matter to get an idea about if you're interested or not. And then, as you rightly pointed out, try to implement those stuff eventually. The best
yeah.
way to learn is,
Eventually, like,
yes.
not immediately, but first you gather interest and then you start implementing. First, you can gauge your interest, that whether you are really interested or not, and then the long and short vision starts coming up. Once you start implementing, then you will also understand that, do you enjoy doing it in the long run? If you feel that no, it's okay, like it's good for just a side project or activity, that's also fine, not a problem.
But okay, for somebody who did that, went through this process, realized that okay, they have got an avid interest in quantum, how can they then build a striking resume maybe? Because that is the first thing that a portfolio of sorts, your proof of work. How do you build something that is able to show off your competence to whatever extent possible in places where you have to eventually be to actually carve out a decent enough career for yourself? Like an undergrad student with not much experience, do not have published research papers or went to international conferences or something, but they want to maybe apply for an internship. So first of all, how do they get past that resume shortlisting stuff? And then eventually what does, because you've, as you said, you've taken interviews, umpteen interviews, What does an interviewer look for in a candidate for a quantum internship?
I think that is more subjective. So it depends from the interviewer's perspective as well, because I don't think like there is a general set format where you can say that, yeah, I'm going to ask only these questions from you, and then if you give right answer, then you are hired or you are selected. Uh, the the thing like for undergraduates like who do not have much experience, the first step is to of course, as he also said, uh, gather literature knowledge, surround yourself with scientific literature. First get to know what the subject is, then also side by side check for career opportunities. It's a nice way to look at the job descriptions of different companies and see like where you are heading. So even as an undergrad, like though the job description says, yeah, we look for masters, PhD, it's okay. Just like you have to start somewhere, right? Like, so undergrad is the stage where you start about these things. And then like once you know, okay, like these are the skills I need, so that can be software, hardware, depends. So based on your availability of resources, you can then define your interest. And once you define your interest, and then you can go to the next step. You can start reading those papers. You can start engaging with the community. So let's say you learn something about quantum, make a video on it, teach it to some, like some kids, or even elders who do not know about the field. uh, Teach it to a class, maybe, like take some lectures or class. You can organize, like everyone can organize these activities in their colleges. I think they're really open to all these activities. uh, you can form societies. Quantum clubs or societies are a really nice way uh, to do this. Participate in open source. That's also another way to show your credibility in quantum to the recruiters who are in undergrad. Because the things which I did, I do not those things are done by people like which have more experience. So if you ask me, like my thing was like I supervised a PhD student even before I did my PhD. Now I don't think like if I say an undergrad that go and supervise a PhD student, I don't think that's a practical tip. So my journey is very different. I supervised a PhD student in quantum machine learning because I was having that experience at that point of time. But even in that, I was facing a lot of imposter syndrome. When I was offered that, I was very skeptical that I don't have the PhD, whether it will be good or not, whether I can really have the candidate graduate, successfully. That's one of the accomplishments of a supervisor. But I was doing mentoring previously. That's why even though I was feeling so much imposter syndrome that I cannot do it, this is not good, but still I took the risk. Then I was a professor, but again I cannot say an undergrad that become a professor and teach engineering and management students about quantum. They will be able to do it. It's not like that, but they will not get a brand tag of a professor, so which they can put on a resume. Because I don't think like companies will accept that, like, okay, you are undergraduate but you are also a professor at a university. How? So that creates a conflict. So the thing is like, implement papers. Once you're implementing papers, you get more ideas, then you can start engaging with researchers with whom you can collaborate to write new papers. Engage in open source, contribute to open source projects, make your own quantum project. So when you participate in open source, even at that time you get a lot of ideas. So then you can make your own quantum project as well. For me, what I do is that I don't make small projects. I convert them into research papers. So either some sort of a benchmarking study, or either some sort of algorithm improvement, or combining classical and quantum hybrid algorithms and creating something new and applying it to an existing data set, and so on. Like there can be different ways of doing research, taking inspiration from other other sorts of literature, like how we do in quantum, like take inspiration from the classical and then implement it in quantum and then see that whether that works or not. Though the experiments are like more like very elementary in nature, but that gives you a good starting point. And nowadays for undergraduates there are a lot of resources. When I was starting, there was no penny lane, there was no Qiskit. Qiskit was in its elementary stages. It was just launched in 2017. But now you have penny lane notebooks, quantum datasets in penny lane. You can run VQE, you can run the advanced version GQE, generative quantum eigensolver. You can do so many things right now with penny lane, and even with Qiskit you can. Now you have like even AI tools at your disposal. We didn't had AI tools, right? uh, like pre December 2022 we didn't had any AI tools, right? So then how are we doing? So now even like students have access to free AI tools which they can use to learn to translate code. First they can try, then they can take help of AI tools to translate code, and then see what sort of new features they can add to that code. So it's highly customizable now. They can even use AI tools for research very carefully, not like blindly depending on AI, but like they can use it very carefully on learning new things, because ultimately it's trained on human data and research papers. They can get suggestions of research uh, with the help of AI tools. Even that's also another way to do things. So I think right now the situation is very nice. Like you have a lot of tools, and undergraduates have a huge opportunity in front of them to use these tools, the resources that are available. Most of the papers are also nowadays open source, so you don't have to pay for a subscription or anything. Even if you need, you can get it from your college or university library. If they don't have, you can always request the librarian to get access for you. So I feel that like these are some of the ways in which they can do. And of course teaching and educating is also a big part, because as you know, we are facing shortage of quantum tech people. um, and you will know this already, right? Like everywhere, like this is everyone's situation, not only India but like globally. There is a shortage in workforce of quantum talent. So I feel that education apart from research is also a big factor in which students can contribute their intelligence.
I agree. I agree. I think in continuation to that, when somebody goes through this entire churning and comes out as a not seasoned but as a relatively better person who has a decent fundamental basis in quantum, then I mean the general path, they go on to do their masters or directly their PhD and so on and so forth. But when you are suddenly coming from a large scale tradition of sorts where you are judged on the basis of the existing content, and then suddenly when you are expected to as a researcher not work or be judged of the existing content but rather what you are able to derive through that existing content in a novel fashion, how exactly do you do that? How do you build or curate or find or discover something new that is pushing that horizon of the known in your particular domain, in this case quantum? So
Yeah, that's
paraphrasing
that's
the
a that's
question,
a
how do you be a good researcher?
Yeah, I completely understand like what you're trying to say. How to be a good researcher? That's a really nice and interesting question I get from even students and even some industry professionals as well. So here is the thing, like good research, like if you want to do good research, that needs some previous experience, and you have to start small somewhere. So I think one of the best ways, so which I mentioned before, is to start implementing papers. Because once you start implementing papers, then let's say you are doing a particular algorithm, then like once you implement it and then once you run it, then you get some ideas because you're deeply researching in that algorithm, you're deeply researching for that topic. Then you automatically get some ideas in your brain that, okay, like I did it in this way, if I do it in some other way, maybe the cost can decrease. I can decrease the cost, or maybe I can decrease the depth, or like whatever optimization parameter you want to tune. So that's one of the ways to do it, implementing these papers. Then another way is like breakthrough topics. How do breakthrough topics happen? So breakthrough topics don't happen overnight. They need years of research, dedication, sincerity, refining your techniques, refining your methods. I mean, if you see any Nobel Prize winner in physics or chemistry, they kept doing that specific sort of research for decades. So that's when it accumulated all together and then reached a stage of breakthrough. So that's uh, one of the ways. So that's about breakthrough, which takes a lot of time. Then what about if you don't have time? So the first step, which I said, implementing research papers. Second step is combine ideas. Like it's now very intuitive right now for many researchers to combine classical ideas into quantum. So for example, CNNs, we know that convolutional neural networks are there, but then researchers came up with quantum convolutional neural networks. And then once you combine that with quantum, then you see what sort of benefit you are getting from it. Because if you're not getting the benefit, then you're not pushing enough. You have to push a bit more. Of course, like failures are completely acceptable, and you have to build some nice relationship with failure, because once you start following this process, then you are going to have a lot of failures in between. Like some algorithms will not work, some ideas which you implemented, they will give worse performance, even in quantum, let's say, or they are too slow to run, then you cannot do it. So there can be many things which can happen. There will be a lot of bugs as well, right? In coding, usually bugs are the things which are the main problems. So you're going to face a lot of those issues, but persistency and consistency, these two things matter a lot, right? You have to be persistent in your effort, but also consistent. That means, like, let's say on Monday my code didn't work, but then on Tuesday, then again I try to make some changes to that code. So that's consistency. So even though you faced failure, you don't back off because of that. So you're still persistent, still you are spending 1 hour daily in that problem. And over the time you will see that your thinking process has matured enough to see different research directions. Another thing I would like to add is that when you read papers, there is always a paragraph which gives future research directions. I really love those paragraphs in the papers, because then those paragraphs are the ones which gives you ideas for your next breakthrough, or for your next paper, or for your next idea to be implemented. So especially reading those paragraphs helps a lot. And this is a really, really useful trick for undergraduates. That first read the abstract, see if it interests you. If it not, reject the paper, go to another paper and see if that interests you. And then let's see the second paper abstract interests you, then directly jump to conclusion, discussion and conclusion, and read those 3 4 paragraphs written there. And in those paragraphs you will see they have reiterated the abstract with the results, like what they achieved in the results section. And then there are one or two dedicated paragraphs for research directions. What are the future improvements that can be done? They can be algorithmic, they can be theoretical, they can be numerical simulation, or for hardware it can be experimental. Not everyone has access to lab, that's why hardware is more difficult. For that you need specialized internship program or something. You need to contact a professor and work in their lab. And that too, I mean, your interest should align with their lab's interest. So many things matter in that hardware case. But for the software you can do it, because nowadays, like you have even companies, for example, like Paperspace, they offer you GPU clusters, right, for $1 or like even $0.5 or something, right? So it's also not impossible to run large models nowadays. I will give you an example. The new algorithm, which is generative quantum eigensolver, it came last year, I think Jan or Feb 2024 sometime. Uh, Very interesting algorithm. You actually train a nano GPT model. You train your own chat GPT. It's very interesting. Uh, and it takes time. It can take a few hours. You can still do it on Google Colab. But let's say if you want to extend it further and generate a lot of quantum circuits where each generated quantum circuit will predict the ground state, and then you accumulate all the results and see whether it can be closer to the true value or not, because the true value is already there by theoretical and experimental results over several decades of research. So then, like, you can train those models now on these GPU clusters for a really less cost. um, and you can always ask your college, your university, to get access to those, and you can work in your lab, like, running these experiments. So I feel that, like, now it's more open, now it's more easy, now you even get access to some really nice resources in a very affordable amount, which was impossible a few years back. So I feel that once you get these ideas and you execute, then you slowly start becoming a good researcher. So it doesn't happen in one day, it's a continuous process, right? You need to keep doing the stuff over a couple of years. You can transition into different fields to get more experience, like how I was doing. I worked in quantum NLP, but then I switched to quantum chemistry, which is something different. And then also explored a bit of quantum ML, quantum optimization. So I really love exploring all sorts of stuff. And now I am doing something very different. Now I am not a chemist, not a NLP scientist, or I don't know, researcher, but like I am doing something engineering related. And the knowledge which I gained in my undergrad on electronics communication, that is going to come handy in doing this sort of research, right? Because uh, then this sort of research is different than the chemical simulations and optimization of routes, maybe, or financial problem like portfolio optimization. So that's more software related. So I think start with software, and then see how it's going. But if you have deep interest in hardware, then contact professors who are working in that domain, and try to get an internship with them, preferably offline, because you would want to work in a lab, right? For hardware, you cannot do it online. I mean, there are things you can do online, right? Let's say the PhD is doing some like measurements in quantum lab, and then they send you the data, and then you take that data and do analysis and so on with Python. That's also very interesting. That also has its own jobs uh, in this domain. But these are, like, different aspects of how you can combine different things together for research. Another example I would like to give, which is very interesting and I personally like, is uh, game theory. So the concept of game theory, like, playing games, like, and winning and losing, that concept, right? Like that thing came from economics. But then, like, when I was in my undergrad, uh, I was like, when I went to, I think I went to IIT Kanpur, and there they were working on cognitive radios and software defined radios, like radio communications, basically 5G signal processing and 5G communications. I was exploring that when I went to IIT Kanpur, and there they were using game theory for optimization of these 5G wireless networks. So can you see the innovation? Game theory is from economics, completely different thing. But now you're applying it, like you basically adapted that game theory model, and now you are applying it for optimization of wireless channels, optimization of wireless networks in 5G communication. This is like really good level of innovation, right? Like you combined these domains together basically, and the linking is game theory. So you can think of ideas like this. It's hard to come also. These kinds of ideas are hard to come. That something is applying in economics, how can I apply in my research? This is hard to come. That's why the best way to start is implementing papers, then open source, then combining different models. Then you can sometime, like when you get more maturity, then you can invent your own model which is better than classical, and then see if you get some advantage over the previously benchmarked ones, and so on. And this is how you slowly go towards a breakthrough, and then this needs to accumulate over time.
And it also really helps, as you said, to get these sort of interdisciplinary ideas. It is very how you use something from this field into this particular work that you're doing. It is very important that you just are trying to keep yourself updated with the general current workings and advancements of different domains. You do not have to go in depth into everything. That is a short way to disaster of doing nothing. But it's always good to just have just know a little bit about different stuff that you are interested about. I mean, I can be a physicist but also be interested in chemistry. I can be a physicist, I
Absolutely.
can be interested in political science. And then having a
Absolutely.
good competent forte in both, I can maybe think about how can we make better EVM machines through quantum cryptography.
Yeah, absolutely. So I mean,
You
that's the point, right? Applying ideas from one domain to another.
yes,
That is the point.
yes,
Yeah.
yes.
And then when you have breadth of knowledge, then that knowledge helps you a lot. And then later on you can refine your knowledge and really decide on which field you want to get expertise in. So for me, I'm doing my PhD in this because I then really felt that, okay, like I have done software, I have the experience, and I can work in that anytime. But now I want to do hardware because I like hardware experience, and like I want to work in labs and see, like, how labs function and how I can engineer stuff, because I have an engineering background. So you can say that I wanted to go back to my roots. My roots were engineering, so let's go back to my roots in
But
my
that is
PhD.
exactly how you find good niches for yourself, right? I
Yeah,
mean, you are able to bring a very unique blend and mix of something that maybe you are the best person at facilitating or coming up with. And that's the
exactly.
brilliant part of this.
Absolutely, like without a doubt, like I'm still very happy, and I don't have much words to express this happiness, but I'm still very happy that I'm working on a blend of this tech where you have neutral atoms, which itself is becoming mature day by day. Superconducting is already very mature, but still lot of research, patents, and everything is going on. And then you have photonic integrated circuit, which is also a very promising and emerging domain. And it like I feel that like it is one of those domains which will be really really popular in the upcoming years, because as electronics got popular because of semiconductor revolution, so same will happen with photonics, and it's already happening. Not like that, it's already happening as well. So I feel that like blending these together, we never know, like, what sort of new physics we can invent from this, because right now we are in nascent stage. We are not thinking about application, though we can apply this device for quantum networking or creating a hybrid QPU out of this, where the photonic integrated circuit can be a link. uh, but then, like, you can perhaps also use it for quantum sensors or metrology applications as well. And maybe beyond that, like we don't know what, maybe in space technology or something, like we don't know. That's the point. So that is also a nice thing, like where X Prize like initiatives come into picture, right? Like, because then they are provoking the emerging researchers to find applications of quantum, because I think we have only a few selected applications, and we are still searching for new application. We still want to know where can we apply quantum. So we never know what comes out of a particular device once that becomes a product, or once it becomes a prototype.
My final question to you for this particular episode is, what would be your word to humanity at large?
Word to humanity at large. I don't know why I find it difficult, but okay. It's a difficult question. What to humanity at large? Okay, let me think about it. So I feel that, like, good, like research, not about like good and bad. Let's not be judgmental, but research in particular should be open source. People should get access to research whenever they want, because that's how the breakthroughs happen. Research cannot happen in closed doors, and once you have this research in open, then you can see novel ideas coming, because, like, always, like, people always think creatively, and, like, they can always come up with new ideas. If you just open source that research, they are able to accelerate the progress of a field, like, really quickly. So I think this is one of the message which I want to give, that open source research is really important. It helped me a lot, and it helped a lot of my students who I have mentored, who are now doing their PhD and masters, uh, and, like, it helped them a lot. But then also another thing is, like, to ask the right questions, and, like, stay away from the hype, because then, like, you can always ask a few of these questions that, like, you are using dilution fridges, but they take like 25 kilowatts of power, right? And an average, like, US home, they consume like 2 to 3 kilowatts, so that's like 10 times more. So, like, what are we doing? So we also need to be power efficient, right, in the end. And I think then that also combines with the sustainability aspect, right? Like, what is the kg carbon dioxide you are producing for that particular logical qubit to work? And I think one of the initiatives by DARPA in the US, that's going to help in this aspect. But then also there is a crunch of helium nowadays, and yeah, Tanzania, China, and even in the USA, there are initiatives where they are taking care of, like, recycling and recovering helium. So we need to focus more on those aspects, because still we are dependent on cryogenics for quantum, especially for superconducting quantum computers. And for other modalities, like, they are slowly going towards room temperature based systems. But again, at certain point, like, you need cryogenic, you need some cryogenic engineering. um, then other things are related to policies, like, how you would make policies in quantum AI, because then in quantum AI, like, once you have ran some experiment, you cannot understand how it came up with the answer. It's something like, it should not be like a black box. Maybe initially it will be like a black box, but then we should try to figure out how to do it. But also we need to be aware that if you take a measurement to figure out something, then it collapses, like, then you lose the essence. So then that becomes hard for policy making, right? Because in policies, then you need to look at stuff where you are really concrete about that thing, that, okay, yeah, this is how this technology is beneficial. So that's also one of the things. So I think asking the right questions is important, and there are a lot of other stuff which I can discuss. One of the important things is about uh, talent building, the workforce building, which I was talking about before. Though it has, like, I mean, it's reaching a good stage because of globalization, I would say. But then you also need to take a look at the divide between the global north and the global south. Is the global south also getting enough opportunities for research? Are they also getting enough funding and so on? So there can be a lot of issues which can be discussed, because I think, like, one of the concerns in global south is related to funding. For cutting edge research, you need really good sustained funding, and then that becomes difficult for global south. Because I went to this conference recently, um, commercializing quantum global. I think it was the fourth annual conference. And there, like, one of the professors joined from Africa, and then he was speaking about this awareness of funding. That, like, we are talking about cutting edge research. It's easy to talk about that, but where will the funding come from, right? And then we need industries as well, uh, which are based on those domains. So I feel that is one of the ways. And then finally, about literacy, you can always do gamification. So right now I'm participating in a program where we are teaching quantum research to school kids. They are just class 10 kids, and the name of the program is Orbits. I'm participating in that program, and we are almost about to end. And there, like, we were teaching them generative quantum eigensolver, which I mentioned you, where you train this nano GPT model, and then that model generates a lot of quantum circuit, and each of those circuits predict the ground state of molecules. And we are teaching them that, and they are generating those graphs results, even though it's at a really beginner level. But it's good for school kids to get exposed to these kinds of cutting edge research and how they impact the daily life, or the industry in general. Because once these kids grow up, then they will be having plenty of new ideas on how to do things, because they are learning it so early. Imagine, like, when we were in school, I don't think we were having this sort of programs, right? Like, where somebody comes and teaches, oh, this is quantum research. You can show something with Bell's theorem. You can see that, okay, there are two photons, but they are giving same sort of properties. Even if you measure them at the last moment in a different basis, it shows you that, yeah, they are entangled. We were not shown, right? So I really like the Orbits program. It is run by a professor in UCL, Professor Abby Bray, Dr. Abby Bray. She runs this program, and I really love this program because of this thing, that you get to teach class 10 and class 12 students, so GCSE and A level students, about these quantum research. And then there are other schools which are participating in other aspects of physics, like astrophysics, uh, chemistry, like all STEM related disciplines which you can think of. They are participating in that, and we are doing it for quantum. So I feel that even in India also, like, we need these sorts of initiatives, right? Because now everything is open source. You have the papers available, you have the Qiskit codes available, Penny Lane, Circ. Like, there are so many things, right? uh, and you can just, like, slowly start teaching them along with basic programming, that how do you use these libraries to create something interesting. Because this is the stage, like, where creative thinking and innovative thinking can start developing. In kids, they have that intuition. When we start growing, then that kind of reduces, because we have seen more world around us. So we become old, and then, like, then we are not able to think that intuitively. But kids, they are very imaginative, and they also ask complex questions which we do not think of. That's what I've observed when I'm teaching kids. And also this is kind of my first time teaching kids like class 10 and class 12. Usually I have taught engineering and management students, and they already have background about stuff like science in general. But what do you do with candidates who do not have that background? How do you develop that background? That itself is challenging in the beginning, to make them understand quantum, uh, why it's helpful, why you should do it, why you should pursue a career in this, and what are the career and job prospects. How can it give stability in your career? That's also an important question, right? Like, you think about stability in any career, whether it will go for a long term or not. But one of the things what I like about quantum is that it's very interdisciplinary. If you have studied like atomic, let's say atomic molecular optical physics, you can also do exoplanet research. The ideas translate to exoplanet or astrophysics or that sort of research. That's why I really like quantum, that you can do a lot of other stuff. It also goes for fabrication, right? So recently in UCL, I fabricated my own resonators. It was a lot of fun. Also, I saw the dilution fridge for the very first time. That was also a awe moment for me. And they have the bigger one actually in UCL physics lab. Like, it's in underground. It's really big. It's really nice. But we fabricated our own chips and so on. It was really nice experience, because I never fabricated my own chips when I was in India. But that was the reason to take this sort of PhD, because I wanted to do it by myself and see how the things work. And then when you do it by yourself, you get so much exposure to that sort of specialized knowledge. And then once you learn fabrication, then it's a transferable skill. Like, you can go and join any other fabrication industry. It's not necessary that you have to be in quantum. So let's say after 5 or 6 years you are not liking quantum, but in your PhD or in your masters you gain some experience in fabrication. You can work for a fabrication based company, right? Skills are transferable always. Same goes with coding too, right? Like, let's say you're not liking quantum software development. uh, you worked on it for, let's say, 3 4 years, and now you're not liking it. You want to go for, let's say, I don't know, like, uh, some finance related company, yeah, some finance basically, like Jane Street like companies, right? You can go there and still utilize your skills. So that's what I love about deep tech. It's so transferable, it's so flexible, that once you learn it, it develops your critical thinking abilities, problem solving abilities, and you can always transfer those into other sorts of jobs. Even if you're switching fields, like you're going from science to arts, like even in that also it helps. And quantum is also about that, right? Like, interdisciplinary, as we were discussing, right? And even you also said interdisciplinary engagement, right? That's why I think you also gave the idea of poetry, right? uh, so I think, and so this is one thing which I love about Google, is that, like, in if you join Google, and I have heard from my friends, their team is very multidisciplinary. They have all sorts of talent in that same room. Quantum research scientists, but on the other hand, UX UI designer, and they are learning quantum. They are learning from the scientists, and the scientists are learning about UX UI, product development, and so on. It's a very, like, tightly knit community. And this is why, like, Google is such a great place to work also, because you get to engage with so many brilliant minds who are experts in their own fields, and then they bring really innovative and creative ideas, and they convert it into products, and which sells well in the market. So I feel that, like, those are some of my points. But if there is anything else, I'm very happy to discuss always, and anyone can reach out to me anytime via LinkedIn or email.
I'm pretty sure there are a ton of different ways we can take a deep dive into and discuss all of these topics in a lot more thorough detail. So, well, that is sort of a segue into inviting you into multiple other future podcast episodes.
Thank you so much. I'm really glad that you invited. I was very happy when you invited me last year, and then I thought, okay, I'm in my training. Let me do it more peacefully when I don't have much work. So right now I'm only in the beginning stage of my PhD, and right now it's a bit more free. We are doing some administrative works and so on. So then I thought I can discuss my ideas peacefully with you, because I don't think I had a podcast as this long as before where I can freely express all of my opinions on different aspects of quantum, whether it's philosophical, whether it's technical, whether it's geopolitical, like anything. But yeah, I'm very happy. Thank you so much for this opportunity.
I mean, the pleasure is all mine. We, even though we really were specified mostly to the technical aspects, I'd really want to talk to you about the geopolitical and the philosophical segments, like completely thoroughly in a good, deep conversation. But yes, for this one,
Let's do
thank
it
you
next
very.
time.
Yes, 100%. Like, obviously, but thank you for this one. Thank you so very much. I
Thank you
am
so
very,
much.
very sure that it will especially benefit the newer folks in the domain at large, because we went a
Absolutely.
deep lot into how can these young folks actually go on about building their careers or gathering competence in the subject matter in general.
Even if they don't want to become PhD supervisor. Not
Precisely.
recommended. I think there are other ways to do it. I think my path was more hard,
Hmm.
because like it's hard to get an opportunity like that. You also have to be, I don't know, little bit of luck or something. But it's hard. It's very hard to do something like that.
Hmm.
So my
Hmm.
path was more difficult. But now with the availability of resources, now like undergrads, masters, they can do a lot. Now everything is possible. Now you have everything in front of you. So now just take opportunity, like take advantage of that.
Thank you so very much for having this
Thank you so
conversation.
much. Absolutely.
And